But this is the part from the 17th group element, that is halogens. These are coming from the halogen, that is the seventh group elements. Here, what are the element present on 7th means fluorine, chlorine, bromine, iodine, and it is called as a astatine. If we know the atomic number of one element, something like in fluorine atomic number 9, then we are able to write the atomic number of chlorine, bromine, iodine, astatine. How? By knowing this magic number 2, 8, 8, 18, 18, 32. See here, how many elements atomic number we have to write now? 1, 2, 3, 4. So 1, 2, 3, and then 4. For this one, just I will add 9 plus 8. This is a 9 is here. Add the plus 8. 9 plus 8, 17 is the atomic number of a chlorine. Then this 17 plus 18. Add the 17 plus 18. Atomic number is 35 for bromine. Then 35 plus 18. Atomic number 53 for iodine. Then 53 plus 32. It become a 85 is the atomic number of astatine. If you know this atomic number of one element, we are able to write the atomic number of other element. By knowing this number, the number will be called as a magic number. Then go with the configuration of it. Configuration of this become fluorine is helium 2s2 2p5. Then it become neon 3s2 3p5. Helium, neon. Then argon. Then krypton. Then xenon. Then it is a 4s2 4s2 3d10. Then 4p5. It is a 5s2, right? It become a 4d10, then 5p5. Here is 6s2, 4f14. It become 5d10 and 6p5. The most important one here is these all the elements are having their valence configuration 2s2 2p5, 3s2 3p5, 4s2 4p5, 5s2 5p5, 6s2 6p5. That means we can say general electronic configuration of this group element is general electronic configuration of this group element is ns2 np5. We can see in ns2 electrons are there, and in np we are having 5 electrons are there, called as a ns2 np5, right? But today in this class about the 17 group element, the part which one I am going to discuss in exam point of view, that one is reactivity of this group element towards the hydrogen. This is a just general part I told you what is there on that, but most important part which one I want to discuss in my today's class, that is the reactivity of these element, reactivity of these element, that is reactivity of sixth group element towards oxygen. That means towards oxygen. Let us say M is an element or any element of 6th A. When it combined with the oxygen, it can form its oxide. It can form its oxide. Let us say it can form its oxide. But question is that, but a fluorine can form the oxide, you know. The oxide formed by the fluorine is a OF2 and O2F2. But among these OF2 and O2F2, which is more electronegative? In both the case, fluorine is more negative. So it cannot be called as a oxide of fluorine, but it will be called as a fluoride of oxygen. Right? These oxides are essentially called as a oxygen fluorides. This is called as a oxygen fluorides. We cannot call as a oxide of fluorine. No, oxide of fluorine fluorides, oxygen fluoride. Why? Because Fluorine is most electronegative element. Among these two oxide beta, OF2 is given here. This OF2, it is a thermally more stable, or we can say it is a thermally stable at 298 Kelvin. They can ask you question, among these two oxide of fluorine, which is thermally more stable? OF2 will be a thermally more stable, right? But in this one more point I will tell you, in both the cases, what is the oxidation state of oxygen? Remember beta, in this case oxygen oxidation state is +2, and in this case its oxidation state is +1. But a fluorine is given here, and fluorine, as it is the most electronegative element, I'll write here fluorine, as it is most electronegative element, its oxidation state is -1. That means fluorine never exhibits positive oxidation state. Fluorine never exhibit positive oxidation state because it is the most electronegative element, and most electronegative element always exhibit as a -1 oxidation state. Chalo, we are discussing about one is a OF2 and another one is O2F2. Sir, OF2 is a thermally stable at 298 Kelvin, right? But here one more is given called as a O2F2, But this O2F2, it has a tendency to oxidize plutonium to plutonium hexafluoride. I repeat, beta. O2F2 will oxidize as plutonium. Pu is a plutonium to the plutonium hexafluoride. For example, this O2F2 we are using, suppose we are having a nuclear spent lie. It is a nuclear spent lie. So what is a nuclear spent lie? We can say, beta, it is a type of the fuel, nuclear fuel. And let us say in this nuclear fuel we are having so many plutoniums are there. This is having a plutonium Pu. It is having a plutonium Pu. But how to remove the plutonium from this fuel is just do one thing. Pass the O2F2 gas on it. If it pass the O2F2 gas, it has a tendency to oxidize Pu into what, beta? PuF6. And remaining that PuF6 came out and O2 came out. Means what we can say, O2F2, it oxidizes, O2F2, it oxidizes Pu plutonium to plutonium hexafluoride, and hence it is used and hence it is used to remove Pu plutonium from nuclear fuel. So this is the most important part I discussed with that. In that one oxide, it is actually not the oxide. It is oxygen fluoride, OF2, O2F2, where OF2 is thermally more stable and O2F2 can oxidize plutonium to plutonium hexafluoride. Now other case not only fluorine, but another one is that chlorine. It also has a tendency to give its oxide. So what is the oxide formed by the chlorine? The oxide formed by the chlorine is a Cl2O, right? Again we can say ClO2, then Cl2O6, and then Cl2O7. See, these all are the oxides of chlorine. But these all oxides of chlorine are how? They all are highly reactive. All are highly reactive, and they act as oxidizing agent, right? Among these all, beta, the most important oxide of chlorine, which one they are asking in the exam about ClO2. Remember, beta, ClO2 is such a oxide of chlorine which is used as which is used as bleaching agent, which is used as bleaching agent. and it is used as a bleaching agent for what? Either for the paper pulp, for paper pulp and textile. Even it will be also used in purification of water. That means for the water treatment. So this is a one more point we wrote. Oxide of chlorine. What is oxide of chlorine? Cl2O, ClO2, Cl2O6 and Cl2O7. Among that they can ask you, among the following which oxide of chlorine, among the following which oxide of chlorine used as a bleaching agent? ClO2, right? Which will act as a oxidizing agent. All will act as a oxidizing agent, but only ClO2 act as a bleaching agent. Now oxide of, sorry, that is a fluoride, oxygen of fluoride we saw, oxide of chlorine we saw, and now we'll see oxide of bromine. Now we'll see oxide of bromine. But oxide of bromine is Br2O will be there, BrO2 will be there, and one more BrO3 will be there, right? One point I will tell you, these all oxides are least stable. That means if they will ask you among all the oxide of halogen, which is a more stable, oxide of iodine will be more stable than oxide of chlorine than the bromine. It is the stability of oxide of halogen. So till now we saw only three. One is a First one is oxygen fluoride. Second one is oxide of chlorine. We can say beta this will be called as a, this will be called as a oxide of chlorine. But the first one cannot be called as a oxide of fluorine because fluorine is more electronegative than oxygen. So it should be called as a fluoride oxygen or oxygen fluoride. And then third one we saw it is a oxide of bromine, which is a least stable. One more left beta, that is oxide of iodine. So it is a BrO2, Br2O and BrO3. They all are the least stable, and they exist at low temperature. So one more question we can get, among the following oxide, which oxide can exist only at low temperature? So oxide of bromine can exist only at the low temperature. And they all are, these all are oxide of bromine. They act as a oxidizing agent. They act as a oxidizing agent. Now the next one left is oxide of iodine. Very important. Oxide of iodine. But oxide of iodine means the first one is I2O4, then second one is I2O5, and one more is I2O7. But I'll tell you these all oxides of iodine are insoluble solids. They all are the insoluble solid. But among these one, this is the most important. Which one? I2O5, right? This I2O5 will act as a good oxidizing agent. Act as a good oxidizing agent, and it is also used, it is also used for the estimation of, for the estimation of carbon monoxide. So I2O5 is a good oxidizing agent, and it is also used for the estimation of carbon monoxide. See beta, once again what we saw, among these one, oxygen fluoride में OF2 thermally stable, O2F2 will be used or it is oxidizes plutonium to plutonium hexafluoride. Then chlorine oxide में ClO2 is a, ClO2 act as a bleaching agent. Then bromine oxides all are oxidizing less stable and they exist only at low temperature. Then come for the oxide of iodine में, the most important is I2O5, which is a good oxidizing as well as used for the estimation of CO. So this one we saw, but among all these one, the important point to remember, among these all the oxide, which oxide is thermally most stable? See, beta, this is the most important point. Oxides of iodine are thermally more stable than oxide of chlorine, than, than that of oxide of a bromine, right? So this is about the, what you can say, the stability of the oxides of the halogen. So we can say higher oxide of halogen tends to be more stable than the lower halogen. So next one will go for the reactivity of these halogens towards the metal. Reactivity towards metal. See here, this M is the element of this one seventh A. M is an element of seventh A means halogen, any element of halogen. And with this element of halogen, M is an element of a seventh A. When they combine with the halogen, it forms the compound called as a halide. Right, beta? I should say MX is the halide. And let us say beta M is a 1A group element. Oh, this no, we can't say like that. It combined with a metal, na. Metal means M is any element of a seventh A. It combined with a metal, and let us say metal which one I am using. Either it is a 1A group or it is a 2A group. For example, beta, if I want to discuss the 1A group metal, beta 1A group metal means M valency plus 1. So we can have metal fluoride, metal chloride, metal bromide, metal iodide. They can ask you this question among these all, which is a more ionic in nature. But I will tell you one small trick for this one to find out the ionic nature. Listen here. One atom should be metal and other atom should be non-metal. But a metal should be more metallic and non-metal should be more non-metallic. If this is the condition, compound become more ionic. Compound become more ionic. But let us say metal common, which is a more non-metallic fluorine. So MF is a more ionic in nature than MCl, than MBr, than Mi. I'll show you this example by giving one more example. Let us say beta here NaF, NaCl, NaBr, NaI, and they will ask you among these which is a more ionic in nature. See beta sodium common. Fluorine I want, chlorine, bromine, iodine, which is a more non-metallic in nature, fluorine. So NaF is more ionic than NaCl, than NaBr, than means we can say in this example, our NaF is the more ionic, but NaI is the more covalent. NaI is the more covalent, right? Same way, one more example I will tell you. But about the covalent nature के लिए, about the covalent nature. Maybe you learn beta this covalent nature in chemical bonding by the rule called as a Fazan's rule. And those who don't know, just try to understand beta. Covalent nature of any compound can be determined with the help of a cation as well as with the help of a anion. Beta, if cation is there, check the polarizing power. If anion is there, check the polarization. But a polarizing power means I will denote PP. Polarization means I will denote P. Means greater the polarizing power, greater the covalent character. And here, greater the polarization, greater the covalent character. For example, I will tell you here. Example for the polarizing power and polarization. See, if the size of cation is small polarizing power will be more. Means polarizing power is inversely proportional to size of cation. And if the charge on cation is more, polarizing power is more. So more the polarizing power, more the covalent character. Come for the anion. Check the polarization. That means here size of anion, or we can say charge on anion. Larger the size of the anion, larger the polarization. Greater the charge on anion, greater the polarization. Greater the polarization, greater the covalent character. Right? Example I want to show you. But what we saw just now, I told you here, the NaF is there, NaCl, NaBr, and NaI. I ask you among these one which is a more covalent. Actually, more ionic kill. This is a trick we are using. Metal should be more metallic and non-metal should be more non-metallic. So it is a more ionic. But now covalent, if you want to check, bole to see here Na common. I'll show you with other example here. See with example among the NaF, NaCl, NaCl, NaBr, and NaI. If they are asking to get the covalent character of the compound, how to get it? But in all these one, Na is common to take out. Then F minus, Cl minus, Br minus, I minus. After that, see beta, these all are the anion, and you know for anion you have to check the polarization, right? Beta, size and charge may check the charge is same now. F will have -1 charge, Cl will have -1. If the charge is same, check the size now. Check the size of the anion. Larger the size of the anion, larger the polarization. That means among this one, iodine will having a iodine will have a larger size. But a larger the size, we can say larger the polarization. Larger the polarization, greater the covalent character. Hence, I can say NaI is more covalent, NaF is less covalent. As the NaF is less covalent, it becomes a more ionic, right? So this is the example I have given based on the reaction of this group element with a metal. But now the a question they can ask you among the following which is a more covalent. See beta SnCl4 and SnCl2. Sn will have a +4, Sn will have a +2. See beta, greater the charge, greater the polarizing power, greater the covalent character. Greater the covalent character. In the same way, PbCl4 and PbCl2, Pb will have oxidation number +4, it will have +2. PbCl4 become more covalent than PbCl2. But the SbCl5 and SbCl3, Sb will have greater polarizing power than this Sb. So greater the polarizing power means greater the charge of the cation, greater the polarizing power, greater the covalent character. Even one more is given, uranium hexafluoride and uranium tetrafluoride. Uranium will have +6 charge, uranium will have +4 charge. So greater the charge of the cation, greater the polarizing power, and greater the covalent character. So this is about just covalent character part we have discussed here. Reaction of this group element with the